Okay. All right. So when we finished last class, we were talking about energy associated with dissolving something. So this was very conceptual and very qualitative. We did put some numbers in there once, but mostly this is a qualitative exercise. When we start looking at actual compounds and asking if they'll dissolve, we're going to use this idea of like dissolves like, meaning polar things will dissolve with polar things. Non-polar things will dissolve with polar thing or with non-polar things. And if they're opposite, then they're not going to dissolve. Okay, that's what like dissolves like means. Everything we've been talking about up to this point is an explanation for this. So the example we did at the very end of class was talking about a polar thing and a non-polar thing, okay? So water and pentane. So pentane has dispersion forces, so it's going to require a small amount of energy to break those apart. Water has hydrogen bonding, so it's going to take quite a bit of energy to break those apart. But when you have one thing that's nonpolar and one thing that's polar, they have to interact according to the weakest molecule. So pentane and water cannot form hydrogen bonding. They can't even form dipole-dipole forces because pentane does not have those significant partial positive, partial negatives. So these guys can only really form dispersion forces. So the amount of energy that they release is really minimal. And so it's just not enough to compensate for all that energy that it took to break apart. So you get this big endothermic gap. So lots of energy to overcome. And so that's just not likely to happen. Whereas if you had something like pentane and heptane, let's just look at that for a comparison. So two nonpolar things. Their number 3, the amount they release when they come together, is also going to be pretty small, okay? So it's pretty comparable to this. It's not going to release a ton of energy. So why does it happen? Well, because the forces that are required to break apart the pentane solute and the, heptane solvent, those are going to be very small. So you're going to have little bit of energy, and then, you only release a small amount of energy, but it didn't take a whole lot of energy to start anyway. So this might be slightly endothermic or maybe exothermic. The point is they're going to be comparable, the amount of energy it took and the amount of energy that it released. So like dissolves like, nonpolar and nonpolar will make those energies comparable. When you have something that's polar and nonpolar, you just can't get those energies to be comparable and you're going to end up not being able to dissolve it. So this will not dissolve. Okay, so this is an energy explanation for why like dissolves like. All right, so when we're talking about this, it's good to know that we have quite a few common solvents that we use in laboratory settings. Obviously, water being a primary one that's polar. There are quite a few others too, alcohols, acetone. This is like home cleaning, whatever, getting crap off of stuff 101. You obviously start with water and maybe soap. Then if that doesn't work, move on to rubbing alcohol, isopropyl alcohol. If that doesn't work, you try nail polish remover with fair warning that you might end up removing more than you intended. I have been known to use nail polish remover and get the thing off the table and then, oh crap, I just removed some of the paint off the table too. So there you go. You have to be cautious with that one. So even amongst polar solvents, there is some variability in what can dissolve in them. But in general, something that's polar is going to be able to dissolve something that is also polar, a solute that is polar. Common non-polar ones, Hexane and toluene, those are both just carbons and hydrogens, so very much non-polar. Carbon tetrachloride, we've looked at this multiple times. Yeah, you've got polar bonds there, but you've got this tetrahedral arrangement. They're all the same amount of polar bond, and so they'll end up canceling each other out. Diethyl ether is a little bit of an odd one because you have, I'm going to do it like the line drawings like I showed you guys about how you will eventually do if you take organic chemistry. So you've got this oxygen stuck in the middle, and then you've got carbons and hydrogens on the side. So this is kind of debatable whether, I mean, this isn't really nonpolar. Every time you add an oxygen in there, you're going to end up with that bent shape, okay? Because you've got the two lone pairs typically, and then the two bonds that are bent. So is that really nonpolar? Well, we're saying it dissolves a lot of things that are nonpolar. So that one could probably dissolve a lot more things that are also polar. So this is going to bring us into this gray area of water is distinctly polar and will distinctly dissolve things that are polar. But there's going to be some things in the middle, like acetone or like diethyl ether, that might dissolve multiple varieties of polarity. So a lot of the questions we're going to talk about are going to be phrased like most likely. So on this next page here, most likely to form a solution, most soluble in water, simply because we can't know for sure until we actually do an experiment with them. Speaking of doing experiments, we've talked a lot about ionic compounds that dissolve in water. Not all ionic compounds dissolve in water, though. You should remember that from Chem 1, that if you have an ionic compound in water, you're going to have to look at the solubility rules to know for sure. So some of these may require way too much energy to break apart those ions and maybe not release enough to compensate. And so there very well will be things that don't dissolve. So when we talk about like dissolves like, we're really talking about covalent molecules, because those are the ones that technically have polarity, right? Polar or nonpolar. Now I realize here I say ionic. Now if you have something that's polar and something that's ionic, so water and salt, it's very possible that it will dissolve, but you really need to consult the solubility rules to know for sure. Okay, so let's practice this. The like dissolves like. I want you to go ahead and answer question 1 and 2 and at least give some thought to question 3. Talk through it with your neighbor, and then we will discuss it together. Remembering that this whole time you're looking at polarity. Oh my gosh, it says it's supposed to be 78 today. Okay, just one more minute and then we'll talk through these. Okay, so the main thing you need to do here is say polar versus non-polar to every single one of these, all right? So ammonia, polar. We've seen that one multiple times. Nitrogen, 3 hydrogens around. Trigonal pyramidal, definitely polar, okay? Isooctane, just a bunch of carbons and hydrogens, so that is non-polar. They're not alike in that sense, so nope, they are not going to form a solution. So when it says, will they form a solution, that means will the solute dissolve, or another way of saying that is be soluble. Okay, water, which is polar, and ammonia, which is polar, yes, those guys are going to form a solution. We see this all the time because ammonia is a common cleaning solution, and you definitely don't use it as just ammonia. It's diluted into water. Okay, sodium chloride, it's not technically polar. We're going to just say, quote, polar. It is more like something that's polar because it has charges, right? Something that's polar has partial charges. Sodium chloride would have full charges. And pentane, carbons and hydrogens. So this is non-polar. No way those guys are going to dissolve with each other. So hopefully you're seeing that we did all the energy stuff, and that was an explanation for why like dissolves like works, but we're not going to use that routinely when we're looking at something and saying, will this dissolve? It's more like background information. Okay, heptane, also nonpolar. Carbons and hydrogens, always just nonpolar. Acetonitrile, this one's a little bit harder. We might have to draw the Lewis structure here. Most of them you won't have to, but let's just take a look. So CH3C, CN. So that one's gonna look like this. So it's very slightly polar, okay? The carbon and nitrogen have a difference of about 0.5. They also don't have a totally balanced structure. You've got carbon on one side and nitrogen on the other. So there is an electronegativity difference there that's not canceled out. So we'll call this polar. It's probably very slightly polar though. So no, these are probably not going to mix. The question says which is most likely to form a solution. I would definitely say the water and ammonia. If I had to pick one to be second, I would say this one, the heptane and acetonitrile. Which this introduces the idea that there is some gray area there. So obviously, even though acetonitrile is polar, it is very different than like water, right? that would be very slightly polar versus water that is extremely polar, so much so that it has the special hydrogen bonding. Okay? All right, toluene is not soluble in water. So what do we know about toluene if we say it's not soluble in water? Is it polar or nonpolar? Nonpolar, right. So if water is polar and they're not soluble, toluene then must be nonpolar. So which of the following is most likely the formula? Well, off the bat, it's definitely not those alcohols, right? Those are much more similar to water. This one, usually when we see oxygens, we can pretty much assume that that's polar. Now, I know that that's not always the case, or at least that's not the dominant force, but 6 oxygens, that's a pretty big part of the molecule. That guy's probably polar, okay? So it's probably not that one. And then when I see this carbon-hydrogen, all that is carbons and hydrogens, that's got to be it, because that one I'm sure is nonpolar. So that one's the most likely. It is the correct formula of toluene. Toluene looks like this. It's a ring, and then it's got a little carbon group sticking off of it. So remember, each one of these represents a carbon, and then they would each have 2 hydrogens as well. Can you tell now why organic chemists do not write out all of the atoms? Because it's just so tedious. So they've come up with this shortened line way of drawing them. Okay, and then question 3 is really getting us into, like I said, this gray area. So every single one of these is an alcohol. So when I look at that, I'm like, well, aren't all of them just soluble in water? However, they also have these big long chains of carbons and hydrogens. So like the first one, 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. So that guy looks like this. So it's got this big long chain of carbons and hydrogens, well, not even big long, but a moderately sized chain of carbons and hydrogens, which really tells us that there's going to be like a side of the molecule that is nonpolar. Nonpolar side, whereas this side is polar. Okay, so what happens is that things that are nonpolar are going to be attracted to this side of the molecule, and things that are polar are going to be attracted over here. And the more chain there is, the more likely you're going to be able to attract things that are nonpolar. So when we look at these groupings, this one, because it has the longest chain, is most likely to be soluble in toluene. Is it actually going to be soluble in toluene? Maybe slightly soluble. But of all of those, that one's the most likely, simply because it has more of those carbons and hydrogens. A really good example of this is soaps. So soaps they're fats. They're like 18, 22 carbons long. Okay, and then on the end, they have this carboxylic acid group, which is 2 oxygens, one of which is an alcohol, okay? So olden days, they would take like animal fat and they would put something in it to neutralize the hydrogen that's on the end there. So they kind of remove this hydrogen. You do that by adding a base. And what you're left with is a very polar end and a very non-polar end. And what happens is if you're trying to get rid of oil on your skin or on the lasagna dish or whatever, that oil gets attracted to this long chain of carbons and hydrogens. So it kind of sticks to that side. And then this polar side sticks to water, and then you wash the water away and the oil goes with it. So prime example of the fact that you can have like sides of a molecule to attract different things. So back to this one, if we had to pick one that would be the most soluble in water, that's going to be the one that is the shortest, where this guy is going to dominate. It's actually kind of funny that we always think of oil and water as being like the classic example of things that don't mix. And when I say oil, I'm thinking like salad dressing, like edible oils. Those have these OH groups stuck on the end here. Like I said, this is like animal fats, okay? So they have those long chains. So yeah, they are non-polar, but they also have this C double bonded to an O, OH group that makes us think that they would be soluble in water, but they're very much not. You can see that by mixing up salad dressing. It does not mix well at all. So it really depends on kind of which side dominates and what the particular thing is you're talking about. That's why we generally use things like most soluble or most likely, because we can't know for sure. Which leads well into this next thing that says often predicting solubility isn't perfectly clear cut. Yes, good to know. Experiments may be needed, okay? So let's look at these vitamins below, and I want you guys to talk amongst yourselves. Vitamins are classified as fat soluble or water soluble. So water soluble vitamins are going to, any excess that you have you're just gonna pee them out. So it's not a big deal if you have too much of them. Fat soluble vitamins, fats again are primarily non-polar. And fat soluble vitamins, if you have excess that your body can't use, it's gonna stick them in your fat stores. And that can be really problematic if you have a lot of excess vitamin sitting in your body. It can be toxic. There's actually, I don't know, I haven't read a whole lot about this with like all the Ozempic and stuff like that, but there is like documented cases where people lose weight too quickly, and when you lose that fat store, all of those toxins or excess vitamins or whatever get released like too rapidly, and it can make you sick, which is fascinating. I would have thought I would have heard more about that recently. I haven't. I started out as a nutritional science major. This is why this stuff is interesting to me. Then I took a biochemistry class and I was like, I hate biology. They don't have answers for enough stuff. They're like, oh, and then it does this thing. We don't really know what the molecule looks like. That drove me crazy. Okay, so look at these molecules and I want you to predict, it's just gonna be a best guess, which ones are water soluble and which ones are fat soluble. Okay, so if you're still looking at it, still thinking through it, I've highlighted any areas of the molecule that have polarity associated with them. So that should give you a good hint. Also, I know from my childhood, because whenever we would be sick, my mom would like hand us a bottle of chewable vitamin C and she'd be like, take one every hour. And I didn't die from toxicity because you literally just pee out any excess. So my guess is that it was not particularly useful, but it wasn't harmful. So water soluble ones, vitamin C would definitely be in that category. You've got those oxygens, you've got lots of alcohols stuck on there. It almost looks a little bit like a sugar. So yeah, vitamin C is definitely water soluble. Vitamin B is also water soluble. Lots of different polar portions kind of nicely spread throughout the molecule. Vitamin K, yeah, it has some polar groups. I don't know, it's getting a lot less there. Vitamin A, that is just like huge chunk of non-polar area with just that tiny little group of polarity on the end. So if I was guessing, I would say for sure vitamin A is fat soluble, probably vitamin K, and then I would guess that C and B are water soluble. So someone looked it up in my last class because I couldn't remember, but vitamin K is fat soluble. Vitamin A definitely is. This is like a classic example of vitamin toxicity. It's not very normal to eat liver anymore, but when people did eat liver, if the animal had ingested a lot of vitamin A, that gets stored in your liver. And then if you ingest that, you're getting like this huge dose of vitamin A, and that can actually be really toxic. The kind of vitamin A that's in like carrots and stuff is not fat soluble. I think it's like, might be ionized or something. I don't remember why, but there's something about the mechanism of it's only the ones that have already been processed and are in animals that are actually fat soluble. Like if you took a pill that was like, oh, that's another good example. Like certain pills, like certain vitamins are dissolved into oils, and then you take that pill. It's like a little gel kind of capsule. That's why. They can't be a solid because they wouldn't dissolve in the water. Okay, so the other section for today is how do we know about how much of these things can dissolve into the solvent? So we're saying, okay, we have a general idea of what will dissolve. Now we need to know, does that mean all of it? Like, can we just add cups and cups and cups of sugar to water and it'll all dissolve? No, I think you guys probably are familiar that at least sometime in your childhood, like making Kool-Aid or lemonade or something, you can't just add a ton of sugar. There's going to be a limit to how much you can add, right? So the amount that will dissolve, once you've added all of that amount, the solution would be considered saturated, and anything else you add would just drop to the bottom. So it's very easy to see with salt or sugar. You stick it in water, you stir it up, some of it dissolves, and then eventually there's no more that will dissolve and it sits on the bottom. Before you hit that point, it's called unsaturated. So when you could add more in there. And then if you guys have ever noticed, I'm sure you have, it's a lot easier to dissolve sugar or salt into a hot liquid. So if you put a spoonful of sugar in tea, it's going to dissolve pretty darn quickly and pretty easily. This is like a common trick in cooking. If you're going to make real lemonade, usually you don't just add the sugar straight to water. You'll put like a cup of water on the stove and dissolve the sugar in like boiling water, or at least very hot water, and then you'll put it into the rest of the mixture. This is called like making a simple syrup, water and sugar. So what you're doing there is that as you increase the temperature, you're able to dissolve more of the solute. So let's say maybe you can dissolve like a cup in, I don't know, a half a gallon of water. If you put that on the stove, you'll be able to dissolve 2 or 3 or even 4 cups in that same half gallon. So increasing the temperature when we're talking about solids almost always increases the amount that you can dissolve, or the solubility. So let's say you do that. Let's say you heat up some water, you dissolve more sugar. So let's say it's the 2 cups in a half gallon, and then you cool it back down to room temperature. So if you'd been at room temperature, maybe you could only mix a cup in, and then you would not be able to dissolve more. But we heated it up, we put 2 cups in, and then we cooled it back down. So it is now holding more of the solute than we normally could have dissolved at that temperature. That's called supersaturated. So it, like I said, it usually involves a process of heating it up, dissolving the stuff, and then cooling it back down. And this tends to be really unstable. So if you have the right conditions, usually this is if there's another crystal of that solid present, the things will start to, we say, come out of solution. So they'll start to reform as a solid and not be dissolved anymore. So again, in cooking, the time, if you've done any cooking, you might have seen this, is if you have one of these syrups, if you're making like candy or fudge sauce or something like that, it can get kind of like grainy and gritty if you aren't careful, because those sugars that dissolved when it was hot started to undissolve when you cooled it down. There's a cute little picture here, fun little picture. So this is a super saturated solution that they start with, and then they introduce a crystal of that same thing into the liquid, and then all of the solute that's dissolved in there starts to crystallize around it because it had had too much of the solute in there at that given temperature. Okay, so for ionic compounds, there's typically very good data on how much can dissolve at a particular temperature. And as you can see, almost all of these increase with temperature. The only one that doesn't, for some reason, is lithium sulfate. There's actually less that you're able to dissolve as the temperature increases. So these are grams of the salt for every 100 grams of water, which is about, what, like a half a cup of water? Yeah, 240 per cup. It's about a half a cup of water. This is the number of grams of salt that can be dissolved in there. And you can see they have very different trends. So all of these salts that we're showing are soluble according to the solubility rules. But how soluble they are is very temperature dependent, and it's also very different based on which salt we're talking about. So there's some calculation questions that I'm going to leave for next Monday. Not next Monday, but 10 days from now. We're going to do those in more detail. I'm just going to give us an example problem here. So let's pretend we've got 2 solutions. One is 25 grams of potassium nitrate in 100 grams of water. And one is 25 grams of potassium sulfate in 100 grams of water. Okay, so look at this table and tell me at room temperature, so at about 20 degrees Celsius, will all of this dissolve? So will it be saturated or unsaturated? That's the real question. Will it be saturated or unsaturated? This amount of salt at 20 degrees Celsius. So this would be good practice for kind of reading this chart. Okay, so I've marked off where the 20 degrees is and the 25 grams, and then we're going to look at the two salts. So potassium nitrate, this is the curve, and this is basically telling you the maximum amount that can be dissolved at that given temperature. So 25 grams, we haven't even saturated that solution yet. So that 25 grams at 20 degrees Celsius would be unsaturated, meaning we could dissolve more. We can dissolve as much as, it looks like 32 grams at 20 degrees Celsius. But the potassium sulfate is a lot less soluble. So at 20 degrees, it can only dissolve 12 grams of potassium sulfate. So that means there's going to be 13 grams sitting at the bottom of the container, undissolved. So that would be a saturated solution, and there'd be a lot of solid left over. Let's see, what about if we went down to like 5 degrees? Okay, salts can dissolve at really low temperatures because, as we're going to learn at the end of this chapter, when you add a solute to a solvent, it actually lowers the freezing point. So even though we might think, well, how can it dissolve if it's at 0 degrees because water isn't even a liquid? Well, if you start adding salt to it, it will be, because it lowers the freezing point. This is why putting salt on the roads works to prevent ice formation. Okay, so pretending now that we're at 5 degrees Celsius, now neither one of those is actually saturated, because potassium nitrate, both of the other way around. Both of them are saturated. Potassium nitrate can only hold 18 grams at that temperature. So now it's got 7 grams that are no longer dissolved. And potassium sulfate is even less soluble now, holding like 9 grams. So there's even more of it that is a solid. So does this make sense, like how the chart works, what it's telling you? You're like, yes, can we please go on spring break? Is this anyone's last class? Oh, really? It's like pretty early in the day. It's your only class. Okay, well, good thing I didn't cancel it, right? Ha ha. Okay, last thing, I promise. So gases dissolving in liquids, exact opposite. The higher the temperature is with a gas, the less can dissolve. The solubility of the gas decreases as the temperature increases. So those gas molecules are held into the liquid by some forces, some intermolecular forces, but they're very easily broken because the gas has lots of kinetic energy. So if you increase the temperature, you're giving it more kinetic energy, and they're just going to be able to escape. So think of 2 cans of your Diet Coke, as the case may be in my life. One that's been in the fridge all night and one that's from the pantry. and you pop the tops, you're going to hear a lot more gas released from the one that's at room temperature. That's because the gas molecules that were in the liquid had lots more kinetic energy, and they escaped into that gap, that headspace. So when you opened it, they all went away. So there is an equation, Henry's law, that allows us to, and these are constants at a specific temperature. So I think these ones are at 25 C. That allows us to figure out how much pressure we have to actually apply in order to get a certain amount of gas into a liquid. So we're going to explain this by doing a calculation. Okay, so they're telling us that, and I don't know, I pulled this question from somewhere, so I'm assuming it's fairly accurate. They're telling us that we want 0.12 molar for this club soda. Okay, so 0.12 moles of carbon dioxide in every liter of water. So that's going to be the S here, the solubility, or how much can dissolve. There's a constant, the Henry's law constant for CO2 at this temperature is 3.4 times 10 to the negative second. And then there is going to be a particular pressure that has to be applied to get the gas to go into the liquid. So this is how they actually probably bubble it through the liquid now that I think about it. But in theory, this is how you would apply, or you would get a gas to dissolve into water, is you would have put a bunch of gas at a very high pressure above the liquid, and then there is a, we haven't talked about the term equilibrium yet, but there is a balance point of how much gas is going to go into the liquid, okay? So calculating this out, this ends up coming out to 3.5 atmospheres of CO2. That is 3 times the pressure of the gas in the room right now. That's a really high pressure just to get carbon dioxide to go into a liquid and get, soda level concentrations. So what they probably do is close off the system at the top in a large container of soda, and then they probably bubble CO2 through the liquid, but what will happen is a pressure will build up at the top of the liquid, and they probably have to maintain that 3.5 atmospheres of pressure to keep that molarity of carbon dioxide dissolved into the soda. They also probably do it at an even higher molarity to account for whenever they pour it into containers. And then they also probably do it at a very low temperature so that not very much of the carbon dioxide will escape. Okay? All right, so that's where we're gonna end. 78 degrees. It's gonna be lovely, and 10 days or whatever it is off. Don't forget to check your email, because like I said, we very likely won't have in-person class on Monday after. Did I mention that before? Okay. So make sure to check your email before making plans on. I'll let you know for sure by Saturday or Sunday. You too?